This is obviously the third talk in the series, so everything in this talk will be joint work with Jan Svart. So I'm going to give a talk which is going to introduce the three words of my title, essentially. So weaves will be something new. Webs are going to be a natural extension of the Brownian web, where we will not specify the distribution of the particle motions. But all of the other properties of webs, the things you wouldn't normally think about, are going to be in there. And flows are going to be a natural way of representing stochastic flows in a pathwise format rather than the traditional format. And it'll turn out that these two things are quite closely connected. So for orientation purposes, I'm always going to have time going upwards. And that has the advantage that in my spatial dimension, left really will be left and right is going to be right. And also I'm always going to include infinities in space. So space has edges attached to it for the whole of the talk. So I'm going to be interested in random sets of Cadlag paths. Okay, so I need to distinguish some special types of Cadlag paths. Firstly, I'm always going to take closed time domains. So a slightly more restricted setup than the really general situation that Jan talked about. I'm going to have two different kinds of paths. So all the paths I'll deal with will be half infinite. So they're going to be, in some sense, forwards in time. So they'll start at a time A, and then they'll run on to time infinity. Obviously, a special subclass of those is paths which are defined for all of time, which are called bi-infinite. And in particular, the sets that I'm interested here have this property, which we've called pervasivity. And that intuitively just means that they cover space-time. And I mean this in the strongest possible sense. So every single point of space-time has to be included in at least one path. And that holds almost surely for all of space-time simultaneously. So by included here, I mean in the sense which corresponds to what we will eventually be thinking of as the M1 topology. And that it just means that you're allowed to be inside a jump, right? On the normal bit of the path, but also if you're jumped over, that counts as well. All right, so how do you represent these things? So stochastic flows classically have been represented with families of functions, whereas the Brownian web we think of as a random set of paths, right? And the way it works in this functional world is you have at a time s and a time t, you have a function that says if your particle was here at time s, then it's going to move to here at time t, right? In the sets of paths world, we have something quite different. We have a single random variable, which is a random set of paths. Over here, we have a whole infinity of random variables, each of which is a random function. So this is analogous to the situation for normal stochastic processes, so what you might think of as single particle processes, right? In the old days, a stochastic process would have been viewed as a family of random variables, one for each point in time, right? And these days we tend to view it as a single random path. Now, this older perspective is in some sense much worse, right? So think about what you would try to mean if you were defining convergence in law in this world here. So what you'd probably come up with was something that looked like for every t, say, xt tends in distribution to xt, right? And these are random variables, single random variables taking values in the state space. And the problem comes from this for all t, right? This is essentially a pointwise type of convergence because you're asking at each t, we want some convergence to happen. And that's very awkward analytically, because if I'm given some set of processes that I'm trying to converge, what do I get out the end? Well, I get an infinity of limit laws, and I don't know how to fit them together a priori, right? So if I want to ask something like, is my limit process continuous? Then in this left-hand world, it's just terrible, right? You need extra conditions and it's hard work. In this right-hand world, when you view something as a random path, you automatically see the regularity properties in the limit, right? So there was a world before Ethier and Kurtz, and basically it was just hard work, right? And so these days we have the Skorohod spaces where we view a stochastic process as a random path in a Skorohod space. and we take limits of a single random variable, and it's just much nicer. Now, stochastic flows have never made the transition from the left to the right. And there's some fairly deep-seated reasons for that, which I'm going to explore a bit in the talk. But let me also explain how the left-hand world ended up. So initially, a flow was something that you thought of as a group action on a space X. Okay, so if I have a function, this is doing the job of saying I'll take particles that need to move for time t. The particle at time x, at state x, is going to move to state phi x. And then if I define phi tx to be phi txt, then these things phi t, if they form a group action on the state x, then that gives you the formal mathematical definition of a flow. And people took that object and then they grew stochastic flows out of that. And so it sort of naturally lived in the functional world initially. And then it's never made the same transition that we made for stochastic processes. And so a consequence of that is that we have no real sense of convergence in which to deal with stochastic flows. Right? So when you see convergence of stochastic flows in the literature, what you'll typically see is something that's saying xst tends in distribution to the limit process, which is problematic for exactly the same reasons as it was problematic when we were just dealing with one particle processes, right? And in fact, worse still, this sense of convergence is not metrizable. So if you want to say how close are my processes, you just don't have a way of doing it. Okay, so one of my objectives in the talk is to take things in this world and move them over into that world. And that's going to mean dealing with stochastic flows without specifying their particle motions. Right, so the talk is going to be largely geometry and analysis more than focusing on any specific stochastic process. Okay, that'll do for that. Okay, so let's explore a bit and think, if we're going to try and represent stochastic flows as sort of pathwise objects, what are they going to have to look like? Actually, this is only on the slides, isn't it? So suppose I have a set of paths, right? So A1 is a set of paths, A2 is a set of paths, A3 is a set of paths, and these are converging in some sense that I want to understand what is sensible to some limit object A infinity. Okay, and suppose that I have a path sitting inside A1, a path in A2, a path in A3. Well, obviously, if these paths have a limit, I want that limit, whatever sense it might be in, I want that limit to sit inside my limit set of paths, right? Now, if I take all of these A's to be the same A, then that immediately tells me that I need to work with closed sets of paths as an absolute minimum, right? Otherwise, my sense of convergence would just not match the stuff what I was aiming for. So that's the first lesson we ought to learn here. We have to deal with closed sets of paths. My next piece of reasoning is going to rely on this diagram here. Actually, I want to draw on it, which is not going to be quite so easy. So let me just put a baby copy of it down here. Okay, so this is a flow of particles where particles are flowing upwards, so forwards in time, and anything which meets this bar here immediately jumps over to this left-hand point and then continues on outwards from there. Okay, now think about what happens if I drop a particle in my flow here, right? So it does that. Now suppose I drop one here, right? It's going to do that. If I drop one here, it's going to do that. And I'm looking for a limit object which looks like that, right? And that doesn't exist as a Cadillac path in the normal sense, because I've got something which is trying to jump at its initial time. Okay, so because we have to work with closed sets, as soon as we want to incorporate jumps, we need to have a better sense of a Cadillac function than the classical world actually has, right? In particular, we're going to have to think of a way to allow paths to jump at their initial time. Okay, so you've already seen our solution to this in Jan's talk, right? So it's this thing called the split real line. Now, we could approach this in a kind of Heath Robinson way, right? We could simply say, let's take the classical idea of a Cadillac path, and then let's just give it some extra arbitrary value, which is its value, if you like, the left limit at the initial time. That would be fine. We could take that as a representation of Cadillac function plus extra number, which does this job here. We could define all the same structure, and we'd end up with something that was absolutely equivalent, but we just have a much worse system of notation, right? So it becomes advantageous to write our paths as functions on this space here, right? So this is, if you like, the space of indexes for left and right limits. So I'm going to say a few things that Jan has said again, and some things that Jan has not said, kind of intermingled with them. So there's a natural order on this space, right? Which effectively comes from our idea of order on the real line, right? We order points if their time coordinate is to the left, and if they have the same time coordinate, then we say minus is less than plus in this sort of natural way. Have you got a hand up? No? Okay. Okay, so that once we have an order, then obviously we know exactly what a closed and an open interval should be. And that actually defines a topology, right? Because we just take the topology generated by the open intervals. So that's called the order topology. The order topology on the real numbers generated by the open intervals of the real numbers, of course, is just Euclidean topology. So this is a quite natural and normal way of putting a topology on something. And of course, we normally understand topologies in terms of what they mean by convergence, right? So Jan has already said this, but let me just remind you. So if I am trying to converge in this space here, if I want to converge to T plus, then what has to happen? Well, the key point is I have to come in from the right-hand side, right? The time things have got to converge, but also I've got to approach from the right. And if I want to converge to T minus, the times are going to have to converge, and I've got to approach from the left. Okay, so this is a space which feels the difference between left and right at a very basic level, right? At a much more basic level than the real numbers do. It has a problem, which sort of immediately comes from the fact that we've got a much more stricter sense of convergence, is that it's actually not metrizable. Right, so there is no metric that generates this topology. In fact, worse still, it's totally disconnected, right? And that comes from something that Jan said, in particular, the fact that if I look at the open interval from S minus through to T plus, that's the same thing as the closed interval from S plus through to T minus. And once you have things that are both closed and open lying all over the place, that just disconnects everything in your space. So this is non-metrizable and totally disconnected. But actually, it's not as bad as you might think because it's very, very close to the real numbers. So in particular, how do we get back from here to the real numbers? So I can define a relation where I say T1 plus minus and T2 plus minus. Let's say these are related if and only if T1 equals T2, right? If I take the split line and I take the topological quotient by that relation, which means we take points that are related and we just pretend they're the same point, right? Then you get straight back to the real numbers. Okay, so this is isomorphic to the real line. So we're not very far away from things that we are familiar with here. And the thing that really makes this a tractable space is the fact that not the Hahn-Banach, the Heine-Borel theorem holds in this space. So the compactness is equivalent to sequential compactness is equivalent to being closed and bounded, right? So we're used to that being true in a metric space because it's true from the metric. In this case, it needs a more trickier proof, but the fact that that's still there allows you to treat this space very much like the real numbers. Okay, so it's quite a nice space to work in once you get over the sort of initial shock of not having a metric around. Okay, and as Jan talked around for quite some time, so I'm going through this quite quickly, essentially continuity on this split real line is equivalent to being CAD-lag in the usual sense. Okay, and that's coming from precisely this, the sense that the space has of left and right limits that the real line lacks. There's nothing fancy going on here, but this does allow us to make use of lots of extra analysis because continuity is a lovely property with lots of theorems and CAD-lag is a horrible property with not very nice theorems. Okay, so this gives us a very elegant way of handling CAD-lag paths. And it also makes them time symmetric, right? Because we've no longer got this issue where the initial time behaves differently to every other time. And here's the proper connection. So I'm always going to stick with closed domains for my CAD-lag paths. In particular, they're going to be from an A- up to a B+. And this is my conception of a CAD-lag function, right? So continuous in the sense of the split real line, which just means right continuous, and its left continuous modification is the thing you think it ought to be. Okay. So I need to build some structure on top of this. So first thing, I'm going to be focusing on interpolated graphs rather than closed graphs. So I want to identify every path, essentially, with the image that it makes in space. And I want the same natural order on this image that Jan has talked about, which generates the M1 topology, right? So this is just a metric that generates the M1 topology written in a format which is quick to present, but it's exactly the same M1 topology as Jan talked about. There's also a natural partial order on these paths, which corresponds to path extension. So in terms of continuous paths, you can draw a very nice picture, right? If I have some path, if I extend it outwards in terms of forwards in time or backwards in time, then that's going upwards in this partial order. You have to be a bit more careful with CAD-lag paths, because suppose I have a path like this and I'm going to extend it backwards, I'm also allowed to extend the jump. Okay. Of course, that problem or that issue doesn't turn up in the continuous world. Okay, so in terms of the graphs, that simply says that the graphs are contained within one another in a way that preserves the time order. For actually almost all cases, preserving the graphs forces preserving the time order, but there's a degenerate case where it doesn't. So if I have a path which is defined on time domain A- through to A+, I could have one that jumps left and another that jumps right, and that's all you see. And I want these two things to be incomparable, and preserving the time order is just enforcing that incomparability. Okay. So I have the Hausdorff metric. So I've got the M1 topology on my path space, and I'm going to fit the Hausdorff metric on top of that. So that's just saying that two sets of paths are closed. If whenever you have a path in one, you can find a close by path inside the other. The trickier piece of structure here is there is also a natural partial order on sets of paths, which in some sense upgrades this order here, but it's a non-trivial way of upgrading it. So I suggest read the intuition first before you try and process the quantifiers. So A is less than B if B covers space-time more efficiently than A. Okay, so I'm going to be always dealing with sets which cover space-time, but the point is that you can do that with fewer paths. If you have some which has covered the same point twice, you might just not need one. Equally, if you have longer paths, that's also better because you can cover more of space with fewer paths. Okay, so if you express this in terms of quantifiers, you get what I've written here, and it takes maybe a little time to parse them, and I think it's not really needed for the rest of the talk. So it's clear that this defines a partial order on deterministic paths, but what I'm actually interested are on random sets of paths. Okay. Now, if in general, in abstract, if you have a partial order which is preserved by convergence, okay, so if I have a space X equipped with a partial order less than or equal to, if Fn less than or equal to Gn, if F converges to F and Gn converges to G, there is a question of does that give you the same partial ordering in the limit? Okay. Now, if this property holds, then you can immediately take a partial order and upgrade it to a partial order that's a stochastic one, right? And the equivalent would be saying two random sets A and B satisfy this relation if there is a coupling under which the relation is almost surely satisfied, right? So you'd say there is a coupling such that almost surely you have this system of quantifiers. Now, our partial order does not satisfy this property, and that's going to be quite important in what follows. So this partial order is slightly well behaved under convergence, but it's not always well behaved. So actually, we have to do a bit harder work, and I'll say a bit later about where that work comes from to upgrade this into a stochastic partial order in the natural way. But that's the partial order that I'm going to be using, right? It's the natural partial order on pervasive sets. Okay, and the next thing I think this has not been talked about at all so far this morning, is crossing. So, of course, you think you know what it means for paths to cross. And when they're bi-infinite, it's fairly easy, right? Two paths are not going to cross if either one is left of the other or it's right of the other, right? And that's fairly straightforward. So of course, I'm expressing this in terms of functions on the split real line, right? So I'm asking if they're jumping, then if one does that, I'm happy for the other one to do that, okay? The left endpoints are ordered in the right way, the right endpoints are ordered in the right way, and so on. Oh, yeah, okay, yes, this should be rotated, sorry. Okay. But it's a bit trickier when you want to deal with half infinite paths, right? Okay, so time is going upwards here. This is obviously a case that should cross, right? One has actually jumped over the other. It becomes a bit trickier when you start dealing with jumps at the initial time, okay? Here, this picture number 3, we have a situation which is pretty much my situation there, right? That shouldn't cross. This one on the right shouldn't cross, but this one ought to cross, okay? And the reason is that in order to make the kind of half infinite idea of non-crossing compatible with the bi-infinite idea of non-crossing, what you should do is say two paths are non-crossing if you can extend them to bi-infinite paths which are non-crossing, right? And that can't be done here because the blue one would crash into the red one as soon as you tried to extend it backwards. Okay, so that's quite a tricky subtlety when you first come across it in the arguments. But let me point out that this means that crossing is not preserved by convergence either. Okay, there isn't much that can go wrong, but what can go wrong is if you have two paths here, right, I can extend that one and I can extend that one and they won't cross. But as soon as I take a limit and move this guy downwards, then in the limit, all of a sudden, I crash into my case 2 up there and my paths start crossing. Okay, so there is this slight trickiness that without extra conditions, taking limits can actually cause paths to start to cross. Okay, actually a good connection to make here is that at some point compactness will come to our rescue, right? Because in order to avoid crossing, this has had to go in and then come back out again. And that's something that the M1 compactness doesn't like, right? So there's going to be an interaction between compactness and crossing. It is preserved for bi-infinite paths, yeah. Okay, right. So I've now built all of the structure that I need to state our main results. So a couple of conventions. So firstly, I haven't strictly imposed it yet, but I do want to stay strictly now. Implicitly, I'm not going to keep saying it, but implicitly, every path is from now on at least half infinite, and of course, Cadlag. And I'm now going to put a compactification on space-time, right? So this is the squeezed space that Jan was talking about. And it's a mechanism for not caring about what happens at the edges, right? I need to care about the direction of time. So I need to distinguish my minus infinity time from my plus infinity of time. But apart from that, I just want to ignore everything that happens at infinity. But the objects I'm interested in here are weaves. So a weave is a random set of paths, okay? And almost surely it has to be compact in the M1 sense. It has to be non-crossing, and it has to be pervasive. Okay, so pervasive is the idea from right from the start that we want to cover space-time. Non-crossing I have talked about. Where is compactness coming from here? Well, I argued that at minimum we needed something that was closed, right? I've already compactified space. That doesn't automatically compactify sets of paths, right? Because, well, even though the space is compact, the set of paths is not compact. But it's not a very big restriction to ask for compactness, and it's coming from the Brownian web framework, where it was discovered to be extremely useful. I do think it's possible that one could build a theory on closed sets rather than compact sets, but I think it would be very tricky. It's not obvious to me how you would go about doing it. So I want to start building some structures on these weaves. So it's this relation here is going to be my biggest tool in building structure onto the space of weaves. And what's sort of underlying this is an expectation that I want to build a weak convergence theory, right? I want to understand, how do I say one random weave converges to another random weave? Weaves are quite complicated objects, so I should expect that the internal structure of weaves is going to have a big influence on that, right? And the way I'm going to realize that is by saying the internal structure of weaves exerts some structure on the space of weaves, which is what this partial order is going to help me do. And then that's going to let me understand how convergence should be working. Okay, so I'm going to distinguish two special types. So a weave which is minimal in the sense of my partial order, I'm going to call a web. So this is the least possible efficient way of covering space. And one that is maximal, so the most efficient possible way of covering space, I want to call a flow. So let me describe the structure that's going to come out here before I put a theorem up for it. So this order is a partial order, right? And in general, a partial order can have a quite awkward structure. Okay, if I take a partial order in general and I pick some element in the middle of it, I might discover there are multiple maximal elements above it, multiple minimal elements below it, and lots of incomparable stuff hanging around in the middle. Now, what's going to happen in the space of weaves is that there will be a unique maximal element that sits, once I've fixed my weave, there is a unique maximal element above it and a unique minimal element below it. So the maximal element I'm going to call F for flow, and the minimal element I'm going to call W for web. And then there's a whole cloud of some comparable and some incomparable stuff that sits in between these two objects. So maxima and minima in this partial order turn out to be in one-to-one correspondence. So that becomes a bit problematic when you start remembering that this partial order and convergence don't interact well, right? Because you start thinking, how do I get from here to here? And you want to sort of walk slowly and take a limit, but that doesn't work because the partial order doesn't preserve, convergence doesn't preserve the partial order. So you have to do the next best thing, which is to use a fixed point operation. So there are going to be fixed point operations that will take a weave and we'll map it straight to its corresponding maxima and straight to its corresponding minima. And I'll tell you what they are a bit later on in the talk. And this pretty much sets up what the structure of the space of weaves look like. Okay, so we have lots of these bubbles, each with a unique minimal and a unique maximal element. So here's the theorem that says this. Okay, so there are functions which, without much imagination, I've called flow and web, which take you to the minima and maxima. So something is a web, so is a minima, if and only if it's a fixed point of this web operation, and something is a flow, if and only if it's a fixed point of the flow operation. But flows have an extra property. You can also say that something is a flow if and only if it's composed entirely of bi-infinite paths. Okay, so that's clearly the most efficient way of covering space-time, right? You're not wasting anything. Every bi-infinite path will be distinct from every other. They all cover a whole thing of space. It's sort of the obviously maximal object, providing they exist, and they always do. And this is the statement saying that there's a unique flow and a unique web attached to each of these things. Okay, so this is a structure that's naturally an equivalence relation, right? Because I want to say, if I'm given two weaves, A and A prime, suppose I'm given this guy and this guy, well, they're not in the same class, so they're not equivalent. This guy and this guy are in the same class, so I want to say they're equivalent, right? So I want to dress these things up as equivalence classes, and so there's a natural relation that does that, where you just say A and B are equivalent if they generate the same web, equivalently if they generate the same flow. Okay. Now, why have I picked the terms web and flow? So I think flow is probably obvious at this point, right? Because a flow is composed entirely of bi-infinite paths. So in some sense, this is the faithful way of giving a pathwise representation of a stochastic flow, right? You see all of the particles moving from time minus infinity through to time infinity. Web is a bit trickier. What is going to happen is that this web operation is going to be something very close to the relation the Brownian web satisfies, right? So this relation W equals WD, which is a fixed point, gives you the Brownian web as a fixed point. And this will start to appear once I've described exactly what the web operation is. But let me first tell you a key idea of how the proof works. Okay, so I'm fast running out of board space. The key idea is that we have some half-infinite system of paths, which may do all kinds of complicated things, right? It might have branches, it might have coalescing. The only thing it can't have is crossing. And what you can do is say, let's take a path in here somewhere that isn't crossing it, and then you can extend it backwards in time without inducing any more crossing, right? And that's actually quite tricky because you can't take a limit, right? Weaves are already closed objects. So if you say, I'm going to try and construct this extension backwards in time by taking a limit leftwards or a limit rightwards, you don't get anywhere because the weave is closed, right? So you just rediscover paths you already had. So this is an unusual case where you have to do some analysis that is not based on taking limits. And this is essentially the hard part of the paper. I can give you some rough explanation of why it's true. So imagine it was going to fail, right? So imagine that you would, as you were moving your path backwards in time, you started to discover that oscillations were appearing in it, right? And if they were bunching up, then all of a sudden you wouldn't be able to generate a Cadillac path anymore. Now, if that was going to happen, then you would need paths above it, which were forcing this thing to go down, and paths below it that were forcing this thing to go up. And as the oscillations bunched up, the upwards paths and the downwards paths would try to be in the same place, and then you'd get one going that way, one going that way, and then you'd have something that crossed. Okay, so actually, to do this reversal in time, it's not anything to do with compactness at this point. It's literally just the non-crossing property and this way of representing Cadillac functions. So this is a proof which is very heavily based on the split real line and proving that the thing that we construct is a continuous function on the split real line. Now, the other thing that has to happen is that this extension has to preserve compactness, right? Because I start with a compact object here, I extend my paths backwards in time, and I get to my flow, and I need my flow to be a compact object. And at that point, we start needing the M1 topology. So the reason for that is that suppose that we end up with something that is kind of doing the bad thing in the M1 topology, right? So suppose that we have a path which has gone up and downwards for all small delta. And what you can do is you can say, because of pervasiveness, I need to have a path that passed through this point. So it's going to have to have done that to be non-crossing, and that to be non-crossing. And I'm going to have had one here that did that. And then when I shrink delta to 0, I end up producing some crossing. Okay, so there's a connection between the M1 modulus of continuity and the way that crossing works that makes it the right sense of compactness in which to do this extension. So obviously it took a lot of fiddling around to find the framework in which this bit worked nicely. And I think that's the most justification I can do without spending hours on it. So once you've got this system set up where you can take paths in A and just extend them backwards, that gives you a system for moving in that direction from your web through to your flow. And that gives you a way of tracing through your equivalence class and building up the whole structure here. So that's the sort of the key element of the proofs. Okay, so next thing I want to do is tell you about the web and the flow operations. So I need a bit more notation to do that. How am I for time? What time do I have to finish? Okay. Okay. So one of the things I want to be able to do is fix a point in space-time, this point Z, and I want to identify the set of paths that pass through Z, right? So that's this AZ here. And then I want to do the same thing for a whole set. So if D is some subset of space-time, then I just take the union of all the paths passing through Z in D, and that gives me all the paths that pass through D. Okay, so this is the analogous piece of notation to what you would recognize as WD in the Brownian web world. And I need to make a distinction between two different types of point. Okay, so what I want to do is distinguish points where I can drop a particle at that point, watch it going forwards and watch it going backwards, and discover that in each direction I have a unique way of moving, right? A unique path. So that can happen in two different ways, right? A point can be non-ramified, which is this idea of having a unique forwards and backwards continuation, by firstly just having a forwards continuation, or by sitting on a path where you already see a path coming in and a path going out. Okay, so the Brownian web world doesn't have very many of these things and thinks they're special. In general, they're not special, right? If you think of the most boring weave possible, where all the paths are just constant, nothing ever moves, actually almost every point is one of these guys, right? But in the Brownian web world, they are quite special. But actually in the sort of general theory, you want to view these two things as the not very interesting ones. And then there are these ramified points where more special things happen, right? Branching, coalescing, and so on. So ramified is coming here from geometry, right? If you remember from the days of complex analysis, right, a function is said to have a ramification point, if I remember rightly, if the function values have to be different on the right-hand side of some branch cut or on the left-hand side of some branch cut. So the functions taking different values is matching onto my word ramified here. Okay. And to generalize this to subsets, I want to say a subset is non-ramified if all of the points inside it are non-ramified, right? So the strictest generalization. So this gives me enough notation to define what I should mean by a particle motion. So the intuition here is I want to just drop points into the flow and watch them move, right? And that generates some distribution. So strictly, what do I want to do? Well, I need them to be non-ramified because I need unique paths for them to move along. Otherwise, my notation is broken. And then if I've got some z, which is m space-time points, then the particle motion from z is just the forwards in time paths from z1, z2, and so on. Okay, so that gives me enough notation to define the web operation. So this is a very mild generalization of what the Brownian web has. So the way it works is you take a dense non-ramified subset of space-time. The fact that you can always find the dense non-ramified subset of space-time is a theorem, right? Essentially saying that most points in space are being very well behaved, but there is some null set out there on which this branching, coalescing, bad behavior occurs. So that's not easy to prove, but it is true. So take some dense non-ramified subset of space, drop a particle at each point in space, and then include the forwards in time motion from that point. Also include all of its, if you like, subpaths, right? So all of the things that sit inside it. So that's just saying, once you've dropped your particle and off it's gone, you also include the path that started there and the path that started there and the path that started there and the one that started there, right? And that's the sort of extra bit that the Brownian web doesn't have to do. In general, weaves can have isolated points inside them. So you need this extra bit in case you've managed to spot an isolated point that wasn't ramified. Otherwise, you end up missing things and it breaks the partial order. But in most cases, this will actually reduce to the Brownian web operation, where you just look at the paths coming out of some space, some set of points D, and then you take closure, right? And this is the closure operation in the M1 topology. So that's the fixed point operator that generates webs from weaves. The one for flows is much simpler. For flows, all you do is you take all the infinite paths that don't cross it, right? And you know that you can find a dense subset of these because of the path extension thing in the previous slide. This one's already closed, so there's no need to take closure for the flow operator. Okay, so essentially this is the structure which takes the place of the partial order not interacting well with convergence, right? The next best thing, if you can't actually take limits, the next best thing is operators that just move you to the minima and maxima. Okay, so that talks about the structure of the space of weaves. So the next thing is a way of characterizing them. So this is moving closer to convergence here. And this is a much nicer, easier to understand theorem. This one is simply saying two weaves are in the same equivalence class if their particle motions have the same distribution, right? So it's exactly the sense of characterization that you would usually want if you're taking limits of a flow-like object, right? Because this is saying if you can identify the limiting particle motions, then you know which equivalence class you're in. And that plugs exactly in. I think I must have changed something at the bottom there. So that plugs exactly into my convergence theorem. Okay, but there is a slight caveat here, which again is coming from this interaction. So if I just deal with flows, convergence of flows in the sense of sets of random paths in law is exactly equivalent to convergence in distribution of finite particle motions. Okay, so for flows, everything works as nicely as you could possibly imagine it. Things are not so nice for general weaves. Okay, so being a maximal object is stable when you take limits. Being a minimal object is not stable when you take limits. So what do you get? If you have a sequence of weaves that converges, the particle motions converge in distribution, as you would expect. But the converse isn't quite true. All you get back is that if the particle motions converge, your sequence is tight, and any limit point is in the same equivalence class, but that's all you get, right? Yep.
Can you say something about the order of? No, you have.
No, they can be non-comparable, I think. So what you're, if you sort of try and wind back to the Brownian web world and see how this is happening, one way in which this can go wrong is if you've produced paths which have managed to enter a dual wedge from its bottom point in the limit, right? So if you know how the Brownian web convergence works, this is sort of capturing what you would get if you can prove the easy bit of the Brownian web convergence and not the difficult bit, right? Which is a situation that some models are in, and which probably many are in, but not many people know about it because you haven't managed to publish it to say, well, it didn't converge to Brownian web, right? And now here's a way of saying, well, it does converge to something, at least in the sense of equivalence classes. Okay, so I think I just have enough time to say a little bit about why this is happening in a sort of abstract level. So the fact that we get a nice world for flows is coming out from the fact that the set of bi-infinite paths is closed, right? If you take a limit of bi-infinite paths, you get back another bi-infinite path, right? So that's essentially, in combination with my structure theorem, that tells you that that being maximal, right, being composed of bi-infinite paths, is actually stable when you take limits. For general weaves, it's not so clear. And at an abstract level, the problem is that if you have a weave, you can remove some paths without changing the distribution of the particle motions, right? When you have a flow, you can't remove a single path and still preserve compactness. But actually, when you have weaves, sometimes you can pick out particular subsets of paths and still get back a weave. And that's what causes this extra difficulty here. That means you end up not sure where you end up in the equivalence class, because you can accidentally generate these extra bits, or possibly not, when you take the limit. Okay. So the very last thing I want to talk about is duality, right? So the Brownian web famously has this property that if you have a forwards in time web of converging, of coalescing Brownian motions, then you can slip into the gaps a system of coalescing Brownian motions that go backwards in time. Now, there shouldn't be an isolated path there. Let's just connect that one onto there. Okay, and you can actually do that in complete generality, which is something to be expected after you've managed to get the path extension working. So the nice way to state this, and this answers the question that was asked earlier this morning, how do you set up duality in these systems? So a dual web is just a web pointing in the other direction, right? So where paths are going from a point in space-time, traveling backwards in time to time minus infinity. And so a double web is when you can take a forwards web and a dual web and couple them in such a way that they're non-crossing, right? So the Brownian double web is an example of this. And if you take any weave, construct its web and its flow, then firstly, there is a double web, right? So you can always fit something into the gaps that goes backwards that is a dual web. it doesn't necessarily have the same distribution, right? So the self-duality of the Brownian web is a happy accident, and I don't yet know what the general condition that makes that happen for other processes is, but it'll be something like saying if your Markov process is reversible or something like that. But I don't have a proof of this. But what I can do in general is the geometric bit, in terms of saying I can tell you nothing about this thing W hat except that it exists and that it's a web. And the way that they get connected together is if you take the web going forwards and the dual web going backwards, and you take paths going forwards and paths going backwards from the same point, and you then clip them together, right, where one starts and the other ends, and you take the set of those paths, then what you get is the flow, right, the set of bi-infinite paths. But you have to be slightly careful here, because when you do this this rewiring procedure, you don't want to accidentally make stuff cross, right? If you think about the sort of points the Brownian web has, where you can have forwards in time paths doing that, and dual paths doing that, right? If I say, okay, let's wire this guy to that guy, and then let's wire that guy to that guy, then I've accidentally caused things to start crossing, right? So you have to avoid doing that. And the neat way to do it is to say, forget about the complicated points, just take the non-ramified ones, wire all of those up. That doesn't go wrong because you know there's a unique forwards and backwards bit from each, and then take the closure, and that closure operation paints in all of the complicated stuff without having to interact directly with it. And I can make lots of other relationships, right? There are other ways you can connect all of these objects together that are kind of in the same style and quite natural, but I'm not going to start making big lists of them. So the very last thing I want to say is a comment on continuity. So I've phrased all of this in the world of Cadlag paths, where I want to allow jumps in the most general possible way. You can project all of this downwards onto the continuous path world, and all of these theorems would be then true, and you replace the M1 topology with the locally uniform topology, and then you get the space the Brownian web would normally be thought of as existing in. And it is then true that as soon as one of these things is continuous, so if the web is continuous, then the dual web is continuous. If the flow is continuous, then the other two are continuous, and so on and so forth. So it all projects down nicely onto a continuous world in the way that you would hope that it did. Okay, that's all my slides. So I'm going to stop there.